What is the first law of thermodynamics? Please, please watch part 1 in order to get a full understanding of this section, if you have not already done so. The link is in the description. In this part, we will learn about the first law of thermodynamics, which is the relation between heat, work, and internal energy. We will look at the differences between isothermal changes and adiabatic changes, derive equations for them, also obtain equations for work done during an isothermal change and an adiabatic change. We will end this section with a number of problems worked out using the concepts. So let's get into it. Well, in the last section we saw that at constant volume, we could say that the quantity of heat that is given to a gas is completely used to change the internal energy. So whatever is the quantity of heat that we give is used to change the internal energy, because nothing is used up for expansion. We don't allow it to expand because it's at constant volume. And therefore, we can write that the internal energy is 3 by 2 nRT, which leads to the change in internal energy being 3 by 2 nR delta T, because the change here leads to a change in delta T. All of the quantities are constants. 3 by 2, N and R are constants. And since Q is equal to change in internal energy, now we can say that Q is 3 by 2 nR delta T. Okay, that's a very important formula. Remember that N is the number of moles, R is the universal gas constant, and delta T is the change in temperature. Let's use this in order to work out a problem. So in this question, a sample of 0.150 kilogram of xenon is in a rigid metal cylinder at a temperature of 20 degrees Celsius. So since it's in a rigid metal cylinder, that means the volume is kept constant. The gas cannot expand. The temperature is 20 degrees Celsius, and then 200 joules of heat is given to the gas. What is the equilibrium temperature? So when 200 joules is given, surely the temperature would increase. So we have to calculate the new temperature. So first we will calculate the change in temperature, and then when we add it to 20, we will get the new temperature. The molar mass of xenon is 131.3 grams, so that is given. Now we will use the formula that we just got. Xenon is monoatomic. That means we are still going to use Q is equal to 3 by 2 nR delta T. Remember that if it was diatomic, it would have been 5 by 2. If it was triatomic or polyatomic, it was going to be 6 by 2. Please go to part 1 to understand how the formulas change. But in this case, xenon is monoatomic, and so Q is 3 by 2 nR delta T. First, we will find the number of moles by dividing the given mass with the molar mass. So the given mass is 0.150 kilogram, and the molar mass in kilograms would be 0.131, right? So if you divide that, we will get the number of moles. So the number of moles is 1.142 moles. And so Q can now be calculated using this formula and rearranging it to get delta T is equal to 2Q by 3 nR. Just a matter of taking it to the other side. And now we can substitute 2 times Q is 200 joules divided by 3 times the number of moles, which is 1.142, times the universal gas constant, which is 8.314. So on doing the calculations, we get 14.04 degrees Celsius. All right, remember that in this case, we could just keep the temperature in Celsius because it's dealing with a change. A change in the Celsius scale is the same as the change in the Kelvin scale. That's why we are able to keep the temperature in Celsius. So once we get the change in temperature, we can find the final temperature just by adding this to the initial temperature, which is 20. So we get 34.04. Now we will look at the first law of thermodynamics, which, as I mentioned, is the relation between the quantity of heat, internal energy, and work. So when we allow heat to enter a system, a gas, a part of that heat is used to increase the internal energy, and another part is used for expansion. So we are assuming that the gas is kept in a container that allows for expansion. So it might be a cylinder with a movable piston, which is completely frictionless. So you have 1 mole of a gas, and then you are giving it heat. So using one part of the heat, the temperature of the gas will increase, which is a change in its internal energy. And then the other part will be used to do work for expansion. So according to the first law of thermodynamics, the change in internal energy is going to be the difference between the quantity of heat given to the system less the work done by the system. So if 100 joules of energy enters a system, and if it uses 30 joules to do work for expansion, then 100 minus 30, which is 70 joules, is used to increase the internal energy. Pretty simple, right? Or the change in internal energy is the difference between the quantity of heat entering the system and the work done by the system. So that's the first law of thermodynamics. But remember that heat can also leave the system. So we have to remember that when heat enters the system, it's taken as positive, and when heat leaves the system, it's taken as negative. So here I'm just telling you that Q is the heat exchanged with the environment or the surroundings. Exchange means heat can go both ways. Heat can either enter the system or heat can leave the system. So it's a heat exchange between the system and its surroundings. And if heat enters the system, it's taken as positive. If heat leaves the system, it's taken as negative. All right. So that is heat entering the system, taken as positive. Heat removed from the system is taken as negative. Now, work. Work can also be both ways. Work can be done by the system, which is when the gas expands, or work can be done on the system, which is when we compress the gas. So if the gas is expanding, work is taken as positive because the gas is doing work. But if we have to compress the gas, then work is taken as negative. So work done by a system is positive, while work done on a system is negative. You got to know that. All right, so that's what, when a gas expands, work is done by the gas, and surely its internal energy decreases because the gas is doing work. We'll get more ideas when we work out problems. So here is an indicator diagram or a pressure volume diagram. It's called an indicator diagram because it indicates the process taking place. So there is an initial state A and a final state B. So the initial state A is here. The gas or the system goes to a final state B. And it can go to that state, excuse me, in two ways. It can either go along this path, or it can go from state A to state B along the other path. So there are two paths taken. Now, remember that heat and work both are path functions. That means heat and work depend on the path taken. But I'm going to prove that internal energy, or the change in internal energy, is not a path function. How does that work out? Let's look at it. We already know that the change in internal energy is the difference. So I'm going to show that the change in internal energy is a state function. That means it depends only on the initial state and the final state. It depends on A and B. It doesn't matter what path the system takes. It can go from A to B along one, or it can go along path 2 or any other path. The change in internal energy will be the same as long as the initial state and the final states are the same. So that's why change in internal energy is called a state function, or it's independent of the path taken. Now we know change in internal energy is Q minus the work. And like I said, Q and work both are path functions. But remember that change in internal energy is a state function. That's a big difference between these three quantities. Next, let us look at the meaning of an isothermal process. The word iso means constant and thermal means temperature. So an isothermal process is a process that takes place at constant temperature. That means the internal energy is constant. Why? Because internal energy is proportional to the temperature. So when the temperature is constant, the internal energy is constant. So what is the change in internal energy? It is zero. So in an isothermal process, number one, the temperature is constant. Number two, the internal energy is therefore constant. That means there is no change in internal energy. An isothermal process always takes place in a system where it can exchange heat with its environment. So heat can go from the system into the environment, and also heat can flow from the environment into the system. Heat exchange between the system and its surroundings is possible, which again means that the system has to be in a container that's a very good conductor, allowing for heat to pass in both ways. So that is an isothermal process. It's a change that occurs at constant temperature. So what you see in the diagram is a cylinder fitted with a frictionless piston here with some weights on top of it. If we remove the weights one by one, then the gas expands. But this expansion is going to be really slow because we are removing the weights one by one. Now this kind of a process is called a quasi-static process. Quasi means false, static means no movement. So it's a false static process. It's so slow that it appears to be not moving at all. So isothermal processes are slow processes. That's what it means. All right, so one of the best examples for isothermal process is the melting of ice. Why? Because ice melts at 0 degrees Celsius. Until all the ice is melted, the temperature does not change. So it's true for any phase change. So all phase changes are isothermal changes. Whether it's the melting of ice or water changing into steam, all of these are isothermal processes. Right? So the temperature is constant and the system exchanges heat with the environment. So those are the two important ideas there. And again, the change in internal energy is zero. But according to the first law of thermodynamics, change in internal energy is Q minus W, and therefore we can bring that in here. And since we also know that change in internal energy is NCV delta T. Remember that? We can set that equal to 0. So now we have Q is equal to work from here because change in internal energy is 0. That means these two are equal. Q is equal to work, which again means that all the heat that's entering is used for work. Okay, that's what it means. And the equation for an isothermal process comes from Boyle's law. Boyle's law is defined at constant temperature. And it states that the product of pressure and volume will always be a constant. So that is the equation for an isothermal process. What does that mean? It means that if you allow the gas to expand to double its initial volume, then the pressure becomes half of what it was. Or if you compress the gas to half of its initial volume, so the volume became half, then the pressure becomes double. Either way, the product of pressure and volume will be the same. That is the equation for an isothermal process. To find the work done in an isothermal process, we start with this basic idea that work is integral V1 to V2 of PdV, but PV is equal to nRT for any ideal gas, which is a constant because it's an isothermal process. So look at that. So we're dealing with an ideal gas. We can apply the ideal gas equation. PV is equal to nRT, but that's equal to a constant. Why? Because all the terms on the right side are now constants. N and R are already constants. T is the temperature, which by definition is a constant, so all three are constants. That's why we say P times V is equal to a constant. Now let's do the integration, but before that we can substitute for P as nRT by V, correct? We can do that, nRT by volume, and then substitute for P here. And when we substitute and integrate, before integration the constants are taken out. So N, R, and T, all three are constants. I've pulled them out, and then you have dV by the volume. Okay? And what is that? The integral of 1 by x dx is natural log of x. So that will be natural log of the volume. And then when you substitute the upper limit minus the lower limit, you get natural log V2 minus natural log V1, which is the same as natural log V2 by V1. Okay? Therefore, we get the formula for work done in an isothermal process as nRT natural log V2 by V1. That is the formula for work done during an isothermal process. So here is a question. It takes 500 joules of work to compress quasi-statically, you see that word again, which means it's an isothermal process. It takes 500 joules of work to compress quasi-statically 0.50 mole of an ideal gas to 1/5 of its original volume. Calculate the temperature of the gas, assuming that it remains constant during the compression. Again, it says that the temperature is constant, so it's an isothermal process. We know, we just got the formula for work as nRT, natural log of V2 by V1. And in this case, work is given. We are trying to look for temperature. So it's just a basic substitution. All right, so we have that, natural log of 1. So how do we get 1 by 5? Because it says if the initial volume is 5, then the final volume is 1/5 of that, so it's 1. Okay, so that's why V2 by V1 is 1 by 5. And then it's negative 500. Why is it negative 500? Look at the question. It says it takes 500 joules of work to do what? To compress the gas. So work is being done on the system. and work done on the system is taken as negative. So that's why it's negative 500. And then on the right side, when you take the natural log of 1 by 5, we're going to get another negative. So that you get negative 6.69 when you multiply these two with this natural log of 1 by 5, and then rearrange to get the temperature, and negative by negative is going to give us a positive. So the answer is 74 Kelvin. So that's how we could use this formula in order to find the temperature during an isothermal process. Now let us look at an adiabatic process. In an adiabatic process, the thermodynamic system is completely insulated from its surroundings, which means no heat exchange is possible between the system and its surroundings. So heat cannot flow into the system from the surroundings, neither can heat flow out of the system into the surroundings. That is an adiabatic process. Since the system cannot get heat, it has to use its own internal energy to do work. So if the gas expands, since it's using its own internal energy, its temperature decreases. If a gas is compressed, then the internal energy and the temperature both increases. So let us look at the adiabatic process. Once again, remember that in an adiabatic process, the system is completely insulated from its environment or its surroundings. No heat exchange is possible. So that is the fundamental definition of an adiabatic process. And then the best example of an adiabatic process would be a rapid process, a sudden compression or sudden expansion of a gas, which gives no time for heat exchange. And in nature, we have thunder. Thunder, which is caused due to lightning, is actually the adiabatic expansion of the atmosphere. The atmospheric air suddenly expands, producing that booming sound. So that is the best example for an adiabatic change. Now, remember, an adiabatic expansion leads to a decrease in temperature because the internal energy decreases and the gas has to use its own internal energy to do work. Now, applying the first law of thermodynamics, which is delta E internal is equal to Q minus work, and because Q is equal to 0, that is, no heat exchange is possible, which gives the change in internal energy is equal to the negative of the work. Again, shows that if work is positive, that is, the gas expands, the change in internal energy is negative. It loses its internal energy. So that's what it means. On the other hand, if work is negative, which is a compression of a gas, two negatives make a positive, so that would be an increase in internal energy. So we got to be careful about how we consider the sign. Okay, so there it is. Work is negative when a gas is compressed, which makes two negatives. That is, the change in internal energy is positive, right? So here is a quasi-static process where you have, a lot of sand on the top of the piston. And if you slowly remove the grains of sand, then the piston is going to come up a little by little. So that's a very small, or slow, I must say, but adiabatic expansion of the gas. So that's why it's called quasi-static. Almost not moving. And then we know that the change in internal energy is CV dt, where C sub V is the specific heat at constant volume. We also know that For an adiabatic process, dq is 0. There is no heat exchange. So that gives the change in internal energy to be 0 minus the work, but the work is given by P dV, pressure multiplied by change in volume. And so now substituting the value of the change in internal energy here, we're going to get CV dt is equal to minus P dV. Rearranging, we get dt is minus P dV by CV. So that is one equation that we get. So what we're trying to do here is trying to get equations that represent an adiabatic process. We'll actually get 3 equations, and that will show or signal the adiabatic change. Next, we will apply the gas equation for 1 mole, which is PV is equal to RT. So PV is nRT, but N is 1 mole, so PV is RT. And then when you take dPV is equal to dRT, and so it becomes PdV is equal plus VdP is equal to R dt. So a little bit of calculus there, because pressure and volume both are variables. You got to hold one constant, differentiate the other, plus hold the second one constant, differentiate the first. So that's how we get that, from which we get dt is equal to PdV plus VdP divided by R. But R, by a Mayer's relation, is Cp minus Cv. R is Cp minus Cv. So we got 2 equations here. The left-hand sides of the 2 equations are the same. So we can go ahead and put the right-hand sides equal to each other. That's what I'm going to do. So here's the stuff that we... So here's what we got. Action. So here is what we had, and when we put the 2 equal to each other, and remember that R is Cp minus Cv. So R is Cp minus Cv. That's why when you cross multiply, you have Cp minus Cv here, then times minus PdV, and on the right side, you have PdV plus VdP times Cv. So that's just cross multiplication. And then when you distribute the terms, we get this. And so the terms Cv and PdV get cancelled. Cv, PdV from both sides get cancelled. All right. And then bringing this term over to the left side makes it negative, so that's equal to 0. And then I'm going to divide throughout by Cv times V. Okay. Divide throughout by that. Okay, actually I'm dividing by CVVP. Cv times volume times pressure. So that makes this quantity Cp by Cv, that's gamma. Cp by Cv is gamma. And then the pressure cancels off and you have dV by V. Here the CVs cancel off, the volumes cancel off, and you have dP by P. So that's why we end up with this relation. Now integrate. Before you integrate, the constant is taken out, so gamma taken out, and integral dV by V, or 1 by V dV, is natural log of the volume, plus you have natural log of pressure is equal to 0. And this can be written as PV raised to gamma is a constant. Because you know that log A plus log B is nothing but log A times B, right? And then instead of, you have natural log V raised to gamma times P is equal to, on the right side, 0 is obtained when you integrate a constant. So that's why you have a constant on the right side. So this is the equation for an adiabatic process. pressure times volume raised to gamma is a constant. Now from this equation we can get two more equations simply by substituting the ideal gas equation or using the ideal gas equation. So these are the three equations, and I'm going to show you how to get the second one, and then you can get the third one in a similar manner. Okay, so these are the three equations. We have three equations because the three variables, pressure, volume, and temperature, all three change, and taking two at a time you can get three equations. So the first one is in terms of pressure and volume, second one in terms of temperature and volume, and the third one in terms of pressure and temperature. So depending on how the problem is asked, you need to select an appropriate equation and work it out. So now let me show you how to get the second one from the first. Now PV is equal to RT for 1 mole, which makes P is equal to RT by V, and I just have to substitute for P here as RT by V. So that gives RT by V raised to times V raised to gamma, and then here this is V raised to 1, which becomes V raised to -1 in the numerator, so that's why we have V raised to gamma minus 1. And then that gives you the constant, because R is a constant, and when you bring it to the right side, K divided by R is going to be another constant. So we don't care about the value of the constant, we just know that it's a constant. So TV raised to gamma minus 1 is a constant. That's how you go from this equation using the simple substitution to the second one. In a similar way, you can get the third equation as well. Now let us find the formula for work done during an adiabatic process. Work done during an adiabatic process. So we start with the fundamental definition of work, which is integral V1 to V2 of PdV. And then because it's an adiabatic change, we use the adiabatic equation, PV raised to gamma is a constant, from where we substitute for P as K by V raised to gamma. And now we can substitute that value, so that gives integral V1 to V2 K by V raised to gamma dV. And then the constant is taken out, and then integration of that gives V raised to minus gamma plus 1 by 1 minus gamma. Because in the numerator this will be V raised to minus gamma. So it's V raised to minus gamma plus 1 by 1 minus gamma. And then the limits V1 to V2. When we substitute the limits, we're going to get V2, so all this outside is the same. Inside, V2 raised to, I just put it as 1 minus gamma, which is the same as minus gamma plus 1, minus V1 raised to 1 minus gamma. All right, so what is K now? We know K is actually PV raised to gamma. So what I'm going to do is, when you distribute the K, with the first term, I'm going to write P2 V2 raised to gamma. But with the second term here, I'm going to write P1 V1 raised to gamma, because K is equal to both of these values. And why do I do that? That is just to simplify, as you will see. So the first value of K there minus the second value of K. So remember that this K has been multiplied with both of these terms, but the K value here is P2 V2 raised to gamma, and the K value along with this is P1 V1 raised to gamma. And that will let us simplify, because you get V2 raised to gamma and V2 raised to minus gamma will cancel out. All right? And therefore we will get 1 by 1 minus gamma, P2 V2 minus P1 V1. That's all we will get. You have P2 times V2 raised to 1, which is P2 V2, similarly minus P1 V1. Now, using the ideal gas equation, PV is equal to nRT. So P2 V2 would be nR T2 and P1 V1 would be nR T1. And therefore, we can now pull out nR taken as common multiplied by T2 minus T1. So this is one formula for finding the work done. Actually, we have two there. So either we can use this to calculate the work done in terms of pressure and volume, or this is the formula for calculating the work in terms of temperatures. So let's try to work out a few problems. Remember that there are four types of processes. Isobaric process is where the pressure is constant. Isochoric is where the volume is constant. Isothermal, temperature is constant. And adiabatic, entropy is constant. All right, entropy constant means no heat enters or leaves the system. So when we do these problems, we need to be aware of what type of change the problem is talking about. That's the most important thing. So here is the first one. Here it says, in a quasi-static isobaric process, so that's isobaric, means pressure is constant, 500 joules of work are done by the gas. If the gas pressure is 0.80 atm, what is the fractional increase in the volume of the gas, assuming it was originally at 20.0 liter? So the work done is given, 500 joules. The pressure is given. We have to find the fractional increase in the volume. So that means we have to find V2 by V1. We have to find the change. And the original volume is 20 liters. So in short, we have to find the final volume first. Find the final volume. Okay, how do we do that? Because work is done and it's an isobaric process, the formula for work in an isobaric process is just pressure times change in volume. That's it. Pressure times change in volume. Pressure is constant. At 0.80 atm, we have to change that into pascals by multiplying with 1 atm, which is 101325. And then liters cannot be used. It has to be in meter cube. 1,000 liters make a meter cube, so I divided 20 by 1,000 to get 0.020 meter cube. That's how you get that term. And then solve for it. When we do the math, we get this on the right side, and the final volume is 0.020 plus 0.00617. So 0.026 meter cube or 26 liters is the final volume. Therefore, V2 by V1 is 26 by 20, which gives 1.3 times. So actually the volume increased about 1.3 times. So remember, we use the formula for work done in an isobaric process. It's just pressure times change in volume. That's how we do that. Let's look at the next one. In a quasi-static isobaric expansion, again, it's an isobaric process. And it looks like it's the same question. It's not. The gas pressure is 0.80 atm. It was originally at 20 liters, same values as before, but here is the catch. If the internal energy of the gas increased by 80 joules in the expansion, how much heat does the gas absorb? So the internal energy of the gas has increased, which means a lot of heat has come into the system. And we're going to use the first law of thermodynamics to do this problem. According to the first law, change in internal energy is Q minus the work. All right? The change in internal energy is 80 joules Work done is 500. Okay. Is the work done positive or negative? It's an expansion. So the work done is positive. That's why the sign did not change. You just have that negative with the work. So negative of positive 500 joules. So that's why you get that. And so the answer is 580 joules. Isn't that easy? It is if you understand what's going on and apply the correct signs. Let's do the next one. In this next question, an ideal monoatomic gas, so it's a monoatomic gas, at a pressure of 2.0 times 10 to the 5 Newton per meter squared and a temperature of 300 Kelvin undergoes a quasi-static isobaric expansion from 2.0 to 4.0 times 10 to the 3 centimeter cube. Okay, so it's an ideal monoatomic gas, and the change is isobaric. The pressure is given, the temperature is given, the initial volume and the final volume both are given. And what are we asked to do? We are asked to find the work done. We did this before. Work done during an isobaric process is simply pressure multiplied by change in volume. So the pressure is given in proper units. Volume has to be in meter cube. And so we have to divide the centimeter cube by 10 to the power 6. So you notice this? 1 meter cube is 10 to the 6 centimeter cube. Because it's 100 times 100 times 100, okay? 1 meter is 100 centimeter. Because it's a cube, you got to multiply 3 times. So that's why we get 10 to the power 6. So once we do that, we will get the answer. And it comes out to be 400 joules. So that's the work done. And in the B part, it says, what is the temperature of the gas after the expansion? Before, it was 300 Kelvin. 300 Kelvin. So we got to find the temperature after the expansion. We use P1V1 is equal to nRT1. The ideal gas equation, P2V2 is nRT2. So if you take the ratios, P1V1 by T1 should be equal to P2V2 by T2. Why? Because N times R is a constant. So this one will become P1V1 by T1. This will become P2V2 by T2. The right-hand sides of both are the same, so we are able to put them equal to each other. And then substitute. When I put the volume, I'm, 2 times 10 to the 3, I'm just leaving it in centimeter cube. It doesn't matter because it's a ratio. And then you have P2V2 by T2. And we can do the calculations. And we get the temperature to be 600 Kelvin. So the temperature is 600 Kelvin. It went up from 300 to 600 Kelvin. I hope you understood that. In the C part, how many moles of gas are there? So now you're actually trying to find the value of N. How many moles of gas are there? So here's the C part. You can simply use the ideal gas equation. Don't you think so? Because we know all the other factors. We know the pressure, the volume, and the temperature. So it's just a matter of substituting those values and calculating. Now we got to be careful. We need to have the volume in proper units. So I'm putting the 10 to the power 6 there. So that is in order to change this into meter cube. So the rest is simple. Pressure, volume, R, and temperature. When you do the calculations, you get 0.16 moles. So there are 0.16 moles. D, what is the change in internal energy of the gas? Let's do that. The change in internal energy of the gas, given by the first law of thermodynamics. It's also given by this formula. See, that's why it was said it's a monoatomic gas. Because if it's monoatomic, we know the change in internal energy is 3 by 2 nR delta T. Remember, if it is diatomic, it's 5 by 2 nR delta T. Okay, so if it's monoatomic, it's 3 by 2. We know all the quantities. We just found the number of moles and R and change in temperature. Change in temperature is 300. How come? Because it went from 300 to 600, didn't it? So the difference is 300. And when we calculate that, we get 599 joules, almost 600 joules. And the last part is how much heat is added to the gas. How much heat? That's where we have to use the first law of thermodynamics. All right, so we have that. And how do we do this? We just got the change in internal energy. We have the quantity of heat coming in as change in internal energy plus work. The work was what? 400. So you get 999 joules. In this question, we have an ideal gas expanding isothermally along AB and does 700 joules of work. How much heat does the gas exchange along AB? That's the first part. In the second part, the gas then expands adiabatically along BC and does 400 joules of work. And when the gas returns to A along CA, it exhausts, means gives out 100 joules of heat to its surroundings. How much work is done on the gas along this path CA? So there are two parts. Let's do it part by part. So in the first part, the ideal gas expands how? Isothermally. Or that means the temperature does not change. Or in other words, heat flows into the system, or heat exchange is possible between the system and its surroundings. That's why it says, it does 700 joules of work. And the question is, how much heat does the gas exchange along AB? What is the change in temperature during an isothermal process? Excuse me. What is the change in temperature? There is no change in temperature. By definition, an isothermal process takes place at constant temperature. If there is no change in temperature, then there is no change in internal energy. Right? Therefore, when you apply the first law of thermodynamics, there is no change in internal energy because it's an isothermal process. We also know the change in internal energy is zero, temperature is zero, change in temperature is zero. So Q is equal to work. Done. Because if this quantity is zero, then Q is equal to the work. You want to find Q? It's exactly the same as the work. So in any isothermal process, the work done will be exactly equal to the quantity of heat exchanged between the system and the surroundings. Now the B part. In the B part, the gas expands adiabatically along BC, and in doing so, it does 400 joules of work. When the gas returns to A along CA, it gives out 100 joules of heat to the surroundings. So two things happen. The gas is expanding adiabatically. That means it has to use its own internal energy to do that work. It did 400 joules of work, so it should have had a decrease in internal energy of 400 joules. Okay, in an adiabatic process, no heat can come into the system, so it has to use its own internal energy. So when it does 400 joules of work, that means its internal energy decreased by 400 joules. And then on top of that, it gives out 100 joules to the surroundings after that. That is during the process CA. So in total, it's lost 500 joules of its internal energy. All right, let's take a look at that. Change in internal energy is equal to the negative of the work. Why? In an adiabatic process, Q is 0. Excuse me. Q is 0, so no heat exchange is possible. So therefore, from here we get change in internal energy is equal to negative work. So that means if the gas does work, it loses that much internal energy. So the change in internal energy is negative 400 joules in the process BC. And then on top of that, it loses 100 joules, like I said. So that's again negative 100 joules. Therefore, the total change in internal energy is, of course, negative 500 joules. And then we have to find the work done. But the change in internal energy is equal to the negative of the work done. So the work done is 500 joules. I hope that's clear enough. So we need to really know what type of process we are talking about and apply the first law of thermodynamics specifically to that process. If it is an isothermal process, there is no change in internal energy. If it's an adiabatic process, there is no heat exchange. So that's what we have to remember. Brings us to this question. An ideal diatomic gas at 80 Kelvin is slowly compressed adiabatically to 1/3 its original volume. What is its final temperature? All right, so it's an ideal diatomic gas. Do we know the gamma or the ratio of specific heats for a diatomic gas? It's 1.4. So we know gamma, it's given. And the temperature is 80 Kelvin. It's an adiabatic process. It's compressed to 1/3 its original volume. What is its final temperature? So here is the relation. Here we have to have the relation between temperature and volume. Remember, there are 3 adiabatic equations, and we will pick the equation that gives the relation between temperature and volume. V2 by V1 is given as 1/3. Yep. T1 is 80 Kelvin. T2 is what we're trying to find. So this is the relation we're using. And then make T2 the subject and calculate. We should get 80 times 3 raised to 0.4. So that gives the answer. So it's because it's 1.4 minus 1 that we get 0.4. So that gives the answer as 124 Kelvin. Last problem in this part. Remember, this is part 2 of thermodynamics. If you have any questions, put it in the comments box. Any suggestions, like the video if you really like it. And then I will try to make it even better. I'll try to answer your questions if you post the questions in the comments. All right, so let's do this problem. An ideal gas expands adiabatically from a volume of 2.0 times 10 to the negative 3 meter cube to 2.5 times 10 to the negative 3 meter cube. You have the initial volume, you have the final volume. If the initial pressure and temperature were 5 times 10 to the 5 pascals and 300 Kelvin respectively, what are the final pressure and temperature of the gas? So you are given the initial and the final volumes, you're given the initial pressure and the initial temperature. We have to find the final pressure and the final temperature. Gamma is given as 5/3. Which is 1.67, which means it's a monoatomic gas. So this is a direct application of the adiabatic equations. To find the final pressure, we will use the pressure-volume relation. rearrange it to make P2 the subject. And we have the values of P1 given in the proper units. And then V1 by V2 raised to 5 by 3. When you do the math, you get 3.4 times 10 to the 5 pascals. That is the final pressure. Now to find the final temperature, we could use this equation and make T2 the subject. All the other values are given in the proper units, so it's a simple. I have not even put 10 to the negative 3. Did you notice here? Because it'll cancel out anyways. So you get the answer as 295 Kelvin. In the B part, it says in an isothermal process. Oh, now if it's an isothermal process and the ideal gas expands from the same volume range, and the initial pressure and temperature were the same, what are the final pressure and temperature? It is actually the same question, but instead of it being an adiabatic change, now what if it's an isothermal change? What is an isothermal change? It's where the temperature remains constant, isn't it? That means the final temperature should be the same as the initial temperature. So that is 300 Kelvin. And now how do we find the final pressure? We use the isothermal equation. What is the isothermal equation? That is the Boyle's law equation, which is pressure times volume is a constant. So we would go P1 V1 is equal to P2 V2. See, the gammas are missing, remember that? And then calculate the final pressure. So that's the initial volume. We're looking for the final pressure, and the final volume is 2.5 times 10 to the negative 3. And on calculation, you get 4.0 times 10 to the 5 pascals. That is the final pressure. And like I said, the final temperature is the same because it's an isothermal process. So that brings us to the end of this part. In part 3, we will talk about the heat engines, the refrigerator, and the heat pump. So that's where we will talk about the application of all of these concepts in building a heat engine, Carnot's engine. And I will tell you how the engine works, what are the formulas that can be used to calculate its efficiency. And then we will look at what is a refrigerator, how it compares to a heat engine. We'll also look at a heat pump. So that will be part 3. And in part 4, coming later on, we will talk about entropy. Remember that during an adiabatic process, entropy remains constant. We will talk about entropy. We will calculate entropy changes. And remember that from each one of these parts, there are multiple questions on the final exam. So if you study these problems in each part, you are going to get a large number of problems on the final exam. All right, so see you on part 3. Thank you. Cut.